Thank you for joining this lesson. We're going to discuss physics paper 2. In preparation for national exams. Remember to subscribe. Remember to share so that you may invite a friend. So let me bring to you the paper for it. So this is the paper, paper 2 that we're going to discuss. And I hope that you guys shall benefit. Remember to subscribe. Remember to share. The questions are here in section 1, 25 marks, and we shall respond to all of them. State the property of light that causes formation of shadows. This is Form 1 physics, rectilinear propagation of light. So the ability of light to travel in straight lines is what makes light to form shadows whenever objects block the path of light. So I hope that one is understood. So we say that this is called the rectilinear propagation of light. The rectilinear propagation of light. This is the property, rectilinear propagation of light. You can just say that the ability of light to travel in straight lines. It is the factor or the property of light which enables it to form shadows whenever objects cross its path. Number 2, name the radiation. Name the radiation represented by A. Name the radiation represented by A. So this is part of the electromagnetic spectrum. And we know that when arranged in terms of increasing frequency, like you can see here, the first one is usually radio waves, then a microwave, then infrared, then we have a UV for the visible light. So we have visible light, then we have a visible light, then the ultraviolet, then we have X-rays, then the gamma rays. There are some acronyms which are used to ensure that students memorize the order of the electromagnetic radiations. So red, radio waves, microwaves, infrared, violet. Then we have the UV, the ultraviolet. This is the visible light. Then we have X-rays and gamma rays. Roasted maize is very unusual Xmas gift. Roasted maize is very unusual Xmas gift. So when a portion has been cut and represented in a figure like this, yours is to check on the left we have the visible light, then X-rays. So which one is supposed to be found? And that is the UV light, the ultraviolet. The UV light. Let's check number 3. A plastic rod is rubbed with a piece of cotton, and it is observed that the rod acquires negative charges. The same cotton is brought. The same cotton is brought near the cap of a positively charged electroscope. Wow, we must be very careful in responding to this. A plastic rod is rubbed with a piece of cotton, it's observed that the rod acquires negative charges. So the rod is now negatively charged. The same cotton is brought near the cup, of a positively charged electroscope. You see now there are three substances here, or three materials here, if I may say. We have a plastic rod. Then with a piece of cotton. So there is cotton here. Then now there is a positively charged electroscope. Now we have an electroscope here, which is a positively charged. Yeah, positively charged. So now, when it is positively charged, it means that positive charges are at this point, both at the plate and at the leaf. We have positive charges at that point, which are leading to an increase in the divergence. Now, we are told that a plastic rod is rubbed, then it acquires negative charges. So this one is negatively charged. Remember, it is not the rod which is being brought at the cap. It is not the rod. We are now bringing the cotton. The cotton, which has ensured that the plastic rod, is negatively charged. This is to mean that the cotton has neutralized all the positives. And to neutralize all the positives, because it was in contact, it means that it was also negatively charged. That is how it ensured that by rubbing the plastic rod, the positives which were on the plastic rod were neutralized, and the plastic rod remains negative. So the cotton was also negative. So now we are bringing a negative. Now it's not touching the cap. The cotton is just brought close now. The cotton, which is negatively charged, is being brought close. So definitely we will have an attraction, though we will not have a neutralization, simply because the cotton material is not in contact with the cap. So there will just be attraction. These ones will just be attraction, and it means that at the leaf and the plate. This one is called the plate. This one is the golden leaf. So at the leaf and the plate, positive charges will be minimized. And when they are minimized, the repulsion which was existing reduces. And hence, the observation that we will make is decrease in divergence. There will be decrease in the leaf divergence. There will be decrease in the leaf divergence. Why is there decrease in the leaf divergence? Positive charges from the plate, the metal plate, and the leaf are attracted by the negatively charged cotton, reducing the repulsion. Hence, a decrease in the divergence of the leaf. Hence, a decrease in the divergence of the leaf. Yeah, you should understand that divergence of the leaf happens due to divergence in the leaf or divergence between the leaf and the plate. This one, the divergence here happens because of similar charges found both at the plate and also at the leaf. Now, when the positive charges are minimized by being attracted upwards, there will be reduced repulsion. There'll be reduced repulsion, and hence a decrease in the divergence of the leaf. Thank you for that. Remember to subscribe kindly. Remember to share so that you may invite a friend. Remember to subscribe and also to share. Remember to leave a comment. Wow, somebody is following from Cowboys, and this is great. Let's share to invite our friends from all over. Thank you for that. All right, we are now being told that the figure below shows 3 capacitors connected between 2 points, A and B. So we have points A and B. If the voltage across A, B is 100, voltage is 100 volts. Determine the total charge. Determine the total charge stored. Determine the total charge stored. Charge Q is usually given by capacitance times voltage. Q equals to CV. That is the formula that we are supposed to operate with. What we will calculate first is the effective capacitance. Effective capacitance. If we call this one capacitance 1, capacitance 2, and capacitance 3, now we can work effective capacitance in this combination of capacitors. When capacitors are in parallel, like C2 and C3, we get effective capacitance by adding the individual capacitances. So we need to write total capacitance between C and C2 and C3. It should be 1.3 plus 0.7. This will give us 2.0 microfarads. Let me write it well. 2.0 microfarads. When 2 capacitors are in series with one another, you know, now that capacitance can be replaced with it now, like between A, whereby we have 2. So the combination of 1.3 and 0.7 becomes another one, which is equivalent to 2.0, and we're also having 2.0. So it's like now we are having 2 capacitors with 2.0, and when they are in parallel and they are only 2, effective capacitance or capacitance total is given by either reciprocals, but if they are only 2, we get their product divided by their sum. Product divided by sum. So 4/4 giving us 1. 4/4 giving us 1.0 microfarads. So the capacitance now effective is going to be given 1.0 times 10 to the power of -6. And now we make it capacitance. Capacitance in the SI units, which is farads instead of microfarads. So now we can talk of Q, the charge stored in the system now, CV. So we need 1.0 times 10 power -6 multiplied by 100. This is going to give us 1.0 times 10 power -3. Because it is charge, the units will be coulombs. Yeah, the units will be coulombs. Thank you for following. I can see you are around and about, and this is encouraging. Let's look at number 5 again from 1. Explain why it is not advisable to leave a lead acid accumulator in the discharged condition for long. One of the precautions that we're supposed to take for lead acid accumulators is to ensure that they are not kept in discharged conditions for a long time. And this is to ensure that, the cells making up this battery that we are calling the lead acid accumulator, they can have the terminals misaligned. So the polarities can be reversed. The polarities of the cells. The polarities of these cells may be reversed, leading to a permanent damage. Leading to permanent damage. And hence, the accumulator may not be recharged. And hence, the accumulator may not recharge again. Yeah, it may not be, or it may never be recharged. Yeah, I think we can use that language. It may never be recharged. It may never be recharged. It may never be recharged. We can look at waves too. The figure below shows the water waves moving towards a barrier. So we can see these are called the wave fronts or the wave forms. The wave fronts. Now the distance between two successive wave fronts gives us the amplitude. It gives not the amplitude. Sorry. The wavelength. So this one, the distance here is called the wavelength. Then we have now the slit in the barrier, or rather the opening, the length of the opening. We usually say if the wavelength is too small for the opening, the waves are going to pass as plane waves, but with slight curves at the end. For example, this is how they will pass. There will be plane waves, but with a slight curving. Then it should be ensured that the wavelength is not interfered with. So how they are spaced before and after diffraction should be sustained. So the gap between the two, the gap between the wave fronts should be sustained. Yeah, the gap is sustained that way. Now, if the slit was too small, for the wavelength, they would have become circular this way. If they were this way, then we have the slit now being too small. They would have become circular, something like that. So please make sure that you don't confuse the two scenarios. So for this one, we are done. We sketch the wave fronts of the wave after passing through the opening. That one is done already. Number 7. Actually, this is the same concept now. Number 7 is the same concept. A person standing behind a wall hears a bell ringing, although he cannot see the bell. Explain. This is because, he's behind a wall. So when sound waves find the wall, sound waves can be diffracted. So the sound waves, the sound waves are diffracted. It's one of the properties. Diffraction is the ability of a wave to curve behind obstacles. The ability of a wave to curve behind obstacles. I hope you are still following and listening to this live broadcast. Thank you so much for being around. Yeah, as we said, you are hereby requested to invite a friend to the broadcast. Kindly invite a friend to this live and powerful broadcast. I hope you are able to see. I just hope that you are able to see. Thank you. Thank you. Thank you. So we are saying that, sound waves are diffracted over the walls, over the wall. Hence, can be detected behind the wall. Then we are saying light does not easily get diffracted. Actually, diffraction of light, yes, it is possible, but it is a rare phenomenon. It is very possible. Light can be diffracted. Light rays can go behind obstacles, but it is a very rare scenario, like the examples of when you look through maybe it's an iron sheet with some little openings, then the sun is overhead. You can see some light trying to emerge through such openings as though they are getting dispersed past the hole. But the point is that it is a rare scenario. Sound waves are frequently diffracted, so they can negotiate a barrier which is on their path, and they get perceived on the other side. Let's continue with the revision number 8 of this paper. Now, in number 8, we are talking of the figure below shows a cross wire strongly illuminated with a bright electric bulb placed behind the screen, just as you can see. Just as you can see. Then what else are we told? We are told that a concave mirror of focal length 20. A concave mirror of focal length 20 is placed in front of the screen. Just as you can see, this is the concave lens of focal length 20. The position of the mirror is adjusted until a sharp image of the cross wire is formed on the screen. Part A, determine the distance between the mirror and the screen. So that one has to be measured. That one has to be measured, and that will be, that one has to be measured. That one has to be measured. And when you measure, when this paper is printed, you can now measure that distance. It means it has been drawn to scale. So from the mirror to where the image has been formed on the screen, we will call it the V. We'll call it the V. Then we measure it. Determine the distance between the mirror and the screen. Just determine it. The image formed is real. The image formed is real. State any other characteristic of the image formed in this case. The image is real. So all real images are inverted. So the image is inverted, among other properties. The image is also diminished. It's also diminished. Yeah, let's look at this case now. Let's look at this case here. Number 9 from 2 physics. Sketch the resultant field pattern around the following current carrying conductors and show the direction of the forces acting on the conductors. So this one is current in. This one is current in. This one is current out. Yeah, that one has to be noted. Current in, current out, into the paper. Into the paper. Then something else that you're supposed to know is that field lines usually move from the north to the south. They never enter the north. So from the north, they move away from north. They move away from north to the south. Move from the north to the south. Yeah, such a movement from the north to the south, like that. They never cross one another. So something you're supposed to understand, if they are moving from north to the south, then we are supposed to know that we can use the Fleming's left-hand rule. Fleming's left-hand rule. This is what I want us to discuss now. When the first, the second, and the thumb are held mutually at right angles, ensuring that the second finger is pointing the direction of current and the first one direction of the magnetic field, then the thumb is going to show us direction of the force. Let us apply this in the second case, the conductor near the south. We will have the first finger pointing this direction. That is the first finger, because it has to point the direction of magnetic field. We will have the thumb pointing upwards, but the second finger that shows us current is pointing where I am, because current is out. For this particular case, current is out. Therefore, the second finger is pointing at me. The first finger is pointing to my right, so that the thumb points upwards. And in such case, we will have the thumb pointing upwards, and that is the direction of the force. So the thumb will point upwards. Then the other case, automatically, the force will be going downwards. So those are the forces, and I have indicated them. So we have applied the Fleming's left-hand rule. Yeah, Fleming's left-hand rule. Let's look at number 10, a good question, which says that a soldier standing some distance. A soldier standing some distance from a wall blows a whistle and hears its echo 1 second later. 1 second later. How far is the wall from the soldier? Speed of sound in air is 330 meters per second. So we're supposed to know that velocity of sound in air is given by, velocity is usually given by half the distance multiplied by, twice the distance, twice the distance multiplied by, divided by time. The reason why we say twice the distance is because once you release an original sound, the instant sound, it goes to the obstacle and it gets reflected back to the observer. So by the time it is reflected back to the observer, it has covered the distance between the source of the sound the velocity of 330 is equivalent to, let me post this. I'm sorry, the screen is misbehaving, but we are getting back strongly. Yeah, there we are. The speed of 330 is given by twice the distance divided by the time taken. Remember, the time is just 1 second. So for us, we are saying 330 equals to twice the distance. To remain with the distance, we have to take 330 and we divide by 2. This will give us 165 meters. So the distance is 165 meters. Thank you for following. Remember that our consultation line is 0704153366. Yeah. Number 11. We are still in section 1 and continuing with our revision. Remember to subscribe. Remember to share. For an invitation, please invite a friend. If there is a friend that you would like them to also succeed, kindly have them on board. Whether they are in secondary school continuing or they are these year's candidates, the content is ripe for everyone. Remember to subscribe. Remember to also invite a friend. Yeah. The diagram in the figure below shows the screen of a CRO displaying the waveform of a certain AC signal. So we can see the alternating current signal has been displayed on a CRO. We also given the sensitivities. Yeah, the Y gain sensitivity is 100 volts per division. Then the time-based control is 1.5 milliseconds per division. Determine the frequency of the AC signal. Determine the frequency of the AC signal. For us to determine frequency, we have to begin by determining the periodic time, and that one will be determined by first interpreting the time-based control, which says that there is 1.5 milliseconds per division. So this means when we come to our diagram now, we should know the time taken to cover a complete wavelength, and a complete oscillation is actually, the diagram has just displayed one complete oscillation. Yeah, one complete oscillation has been displayed. So what time is going to be within here? What time is going to be within here? How many divisions do we have? We have a 1, 2, 3, 4, 5, 6, 7, 8. 8 divisions within a complete oscillation. 8 divisions only. So with 8 divisions, and per division we have 1.5 milliseconds. You know, we say that a periodic time is given by a time-based setting multiplied by number of divisions in one complete cycle or a complete oscillation. So what does this mean? That we need 1.5 milliseconds per division multiplied by 8 divisions. So the divisions are cancelling, so that we have, when we multiply this 1.5 by 8, I'm getting 12 milliseconds, which means with 12 milliseconds, we can convert this to 12 multiplied by 10 power negative 3 seconds. So now we have it in SI units, seconds now. And if these are seconds now, how do we get frequency? How do we get frequency? Small letter f. Frequency is given by the reciprocal of periodic time. So 1 out of 12 times 10 power negative 3. So this is going to be, when we take the reciprocal of this, I'm getting 0.0833, then I multiply by the reciprocal of 10 times negative 10 to the power of negative 3, which becomes 10 power 3. To multiply this by 1,000, I'm getting 83.333. Being frequency, the SI unit is given as hertz. We continue now to number 12. State one reason why a CRO is more accurate in measuring voltage over ordinary voltmeters. These ones, they even give, they can display records. The voltage is displayed continuously. So we can monitor how the voltage is changing. Also, we also say that it is also more accurate. It's more accurate than the ordinary voltmeter, since it measures a bigger current, a bigger voltage, sorry. Remember, the ordinary current will rely on the deflection, whereby it is limited to some levels of voltage. When connected to very high voltages, the voltmeter, which is ordinary, can break. The pointer can break. Since it is limited. Well, let's look at this on domestic wiring. A house is supplied with 240 volts from a power source, which is fitted with 13 amperes save fuse. Determine the maximum number of 60-watt bulbs that can be fitted in the house. All right, we know that because it is going to operate at 240 volts and the power of a bulb is this, we can check the current. We know power is given by VI. So what about current? Power divided by V. So 60 out of 240. This gives us 0.25 amperes. So each bulb is drawing current equivalent to 0.25 amperes. 0.25 amperes. All right, with that current, and now we are having 13 save fuse. You know, the rating of the fuse is supposed to be slightly above that of the electrical device which is being used. Therefore, for 13 amperes, how many devices rated 0.25 are going to be found? I'm having 52 bulbs. So 52 bulbs will require current equivalent to exactly 13. But now we are saying that the devices must be having a currency or current demand slightly below that of the, not equal to the fuse and not above the fuse, slightly below. So, to the best of my knowledge, now this fuse is supposed to be loaded using 51 bulbs. Because when we use 52 bulbs, they will demand 13 amperes, which is an equivalence of the fuse. and the current of the appliance should be slightly below. So we operate with 31 of them. 31 of them. Wow, let's look at the section 2 of this wonderful paper. The figure below shows 3 resistors connected to, or connected as shown. Connected as shown. The first part is telling us if the voltmeter reads 5, the voltmeter here, this one is reading 5 volts, we find the part 1 effective resistance. Let's get effective resistance first. We have a resistance here of 6 and another one of 3, and they are in parallel. So effective resistance there between, we can say, sorry. Okay, yeah, we are back. All right. So we're supposed to know if this one is led to be maybe resistor 1, then resistor 2, then resistor 3. Finding effective resistance means for 2 and 3, we will be having a 6 and 3, yeah. 6 by 3 divided by 6 plus 3. This is 18 out of 9, giving us 2 ohms. Giving us 2 ohms. Now with 2 ohms there, it will be like now we have 2 ohm and 8 ohm. So, and they are now in series. We are reducing R2, R3 to 1, which is having 2 ohms. So that now, that one together with 8, which are in now series, they will be added. So 2 and 8, giving us 10 ohms. Yeah, giving us 10 ohms. 10 ohms. Number 2, potential difference across the 8 ohm resistor. Potential difference across the 8 ohm resistor. Let's get back to our diagram. We're supposed to know that through the 3 ohm resistor, we will also be having 5 volts voltage. Reason being, the 2 resistors are parallel to one another, so they are at the same potential. There is also 5 there, the same potential. So we can get the respective resistances now. We have resistances, sorry. We can get the respective currents. So current in the current 2 or current in the 6. You know, current is given by, from this, V equals to IR. So current will be given by V over R. So a V, which is equivalent to 5 out of a R, equivalent to 6 amperes. Then current across the 3 is also going to be V there out of 6 amperes. What about the total current now passing through the 2 of them? Effective current, total current, the effective current now in the system. Current in the system shall be 5 over 6, 3 over 6, and this is giving us what? 1 1/3, which is 1.33 amperes. Yeah, 1.33 amperes. Remember, in a parallel setup, when current is total at this point, it gets split now through here and also through here. So through the first case, we will have 5 over 6, and the other case, we will have 3 out of 6. Wait. I must correct that. V over resistance. So V is 5. In this case, V is 5 out of 3. Yeah, 5 over 3. 5 out of 3. So we are adding, I'm sorry for that mistake. In the second case now, V 5/6, then 5/3. Let me check the summation. 5 out of 6 plus 5 out of 3, giving us a current of 2.5 amperes. 2.5 amperes. So the 2.5 amperes is the one now being split into 5/6 to be here and 5 out of 3 to be here. Yeah, 5 out of 3 to be there. That means now current total now. So there is 2.5 here. 2.5 entering the system, 2.5 amperes. Then it is split now depending on the different resistances. So if we have total current, that is the same current flowing through the 8 ohm resistor. And for the 8 ohm resistor, we can get, for the 8 ohm resistor, we can get V by taking current there multiplied by the resistance there, 8. What is the resistance there? 8. So multiplication will give us 20 volts. 20 volts. So I hope we are together in that computation. Otherwise, thank you. Thank you. Thank you very much. Yeah. Wow, number part B of this question. State the Fleming's right-hand rule. Thank you guys for being around. I request you to subscribe. I request you to share. Request you to invite friends to this powerful live broadcast. Otherwise, we can continue learning. Can just continue learning. State the Fleming's right-hand rule. And this states that when the first, the second, and okay, when the first, you know, they are fingers, we can mention them independently actually. First finger, second finger, and the thumb of the right hand. That one is very key. Are held mutually at right angles. Mutually at right angles. Mutually at right angles. Then with the thumb pointing motion of the conductor, we say the thumb points to the motion of the conductor. I hope you guys are following. I hope everything is well. To the motion of the conductor. The first finger points to the direction of the magnetic field. The first finger points to the direction of the magnetic field. and the second finger points the direction of current. The direction of current. The direction of current. Yeah. Yeah, the second question now. The diagram below shows two circuits placed close to each other. Primary coil, the secondary coil, then we got a galvanometer and a switch K. The question is, state the observation made when the switch is closed. Due to mutual induction now, we will have due to mutual induction, we will have a potential difference, an EMF induced in the secondary coil. Then we will have now current flowing. The current flowing will be detected by the galvanometer. So you say that the galvanometer deflects. The galvanometer deflects in one direction then back to zero. That one is very clear. You must state that back to zero. Without back to zero, actually you're going to be wrong. That will be a wrong observation. Back to zero, because once the magnetization reaches saturation, there will be no more magnetic flux linking. There will be no more magnetic flux linking. And then without magnetic flux linkage, then we will not have any induced EMF on the other side, and the current will not continue following, and the galvanometer has to get back to zero. So it will deflect to a maximum and back to zero. State and explain the observation made when the switch K opened. Now, when you opened it, the galvanometer deflects in the opposite direction. The galvanometer deflects in the opposite direction, then back to zero. Then back to zero. Deflects in the opposite direction, then back to zero. Then back to zero. Why does it happen so? This is because when switched off, or when K is switched off, the magnetism in the primary coil dies off, leading to an EMF in the opposite direction. In the opposite direction. Another good question about transformers. The figure below shows a transformer which is 92% efficient. That is used to transmit power to a 12-volt 36 watts bulb. Yeah, 12 volts 36 watts bulb. Determine the current in the primary coil if the bulb is operating normally. So we're supposed to know that power output divided by power input expressed as a percentage should give us efficiency. So the efficiency of 92%. Okay, how do we get power input and power output? You know, generally electrical power is given by VI. So power output shall be the output. It's already given. Power output in watts. It's already given as 36 watts. What about power input? Power input is the power in the primary, which has not been provided, but it can be given by the voltage there multiplied by the current unknown. Multiplied by the current unknown. So we will now write our formula 36, which is the output. Our output is 36, divided by 240, multiplied by a known current in the primary. Expressed as a percentage should give us 92%. Now with this, we can get the current in the primary by taking a 92 multiplied by 240 divided by 36 and 100. This will give us exactly 6.0 amperes. 6.0 amperes. 6.0 amperes. Yeah, 6.0 amperes. I hope I've carried out the multiplication clearly. And the division, 92 by 240, then we divide by 36 and 100. Okay. We can continue working out the questions. We can continue working them out. We got a part D here. Explain why long distance power is done at very voltage. Okay, you know, for voltage to be stepped up, current has to automatically be stepped down. For there to be a stepping up of voltage, current automatically is stepped down. And with that knowledge now we're supposed to know that when there is a stepping up of voltage, current is down. Therefore, the heating effect during transmission in the cables is going to be lower, and hence power loss is minimized. So this is to minimize power loss. This is to minimize power loss, which is caused by, which would be caused by, low voltage transmission, which means high current. So it's good for you to know this means low current. Yeah, it's good for you to have that basic information. Very good for you to have it. Wow, we are still doing it at number 15 now. It's number 15. At number 15, the examiner is advising us to define the term half-life. This is the time taken for a quantity or a substance. The time taken by a radioactive substance to reduce to, not to reduce to, okay, we can say to decay or to decompose to half its original its original amount. The time a substance takes to decay until it is half, or to decay by half its original amount. Might be original mass, might be original number of particles in that given substance. As long as it is up to half the original amount that we had at the beginning of the decomposition process, then we shall talk of a half-life. That period is called half-life. That time is called half-life. At part B of this, the activity of a radioactive substance initially at 640 counts per second reduces to 40 counts per second in 42 minutes. 72 minutes, that is, in 72 minutes. Determine the half-life of the substance. Determine the half-life of the substance. How do we get half-life? All right, there is this formula that tells us that the remaining substance, either mass, number of particles, is usually given by the original NO multiplied by half, and half is raised to small letter n. You know, n is the number of half-lives now. So 40 equals to original 640 into half raised to n. Mathematically, we can divide through by 640, giving us 1 out of 16, being equivalent to half raised to n. So 1 over 16 can be written as half raised to 4 equals to half raised to n. And this one automatically now can be concluded that because the bases are the same, then the number of half-lives equals to 4. Now, the number of half-lives being equal to 4, and we are told that they took place in 72 minutes. How much is one half-life? How long is a half-life? So 72 out of n to give us 18 minutes. This gives us 18 minutes. That gives us 18 minutes. Alternatively, actually, this question can be worked otherwise. We can talk of an alternative. Alternatively, we can have, we are beginning from 640. Then this composes up to half, which is 320. Then again, decomposes to half, which is 160. Then decomposes again to half, 80. Then finally decomposes to 40 counts. Then finally decomposes to 40 counts. So what we are saying is that for a substance to reduce from 640 counts, 640 counts per second, or per second, all the way to 40, there are the first, the second, the third, and the fourth half-lives. So in 72 minutes, there are 4 half-lives: the first, the second, the third, the fourth. We have 4 half-lives within 72 minutes. So we need to take 72 out of 4, and we still get our 18 minutes. Still get our 18 minutes. So that's how we work it out. There is the part C now. We can now respond to our part C. The figure below shows a Geiger-Müller tube, the GM tube. Geiger-Müller tube. Now in the GM tube, what is the question here? I think we can see the high potential there. You can also see the cathode, which is the metal cylinder. We can also see the anode. Then there is a argon gas at low pressure plus halogen vapor. Halogen vapor. Then there is the Mika window. Part one of the question. Part one of the question. Give the reason why the Mika window is made thin. Give the reason why the Mika window is made thin. The Mika window is made thin to allow emitted particles or radiations into the tube for detection. To allow emitted radiations into the tube for detection. One thing you're supposed to know is that the emitted radiations, we place the radioactive substance here to be placed somewhere here so that it emits radiations and they are detected by the GM tube. We're supposed to know that these particles being emitted have what we call penetration abilities or penetration power. It is not all the penetration powers which are equal. And if penetration power can be little, then the Mika window, which is supposed to allow them to enter for detection, is supposed to be thin, so that the one with the least penetration ability, that is the alpha particles, which have very little penetration ability, they can at least be allowed in and get detected. They can at least be allowed in and get detected. So the purpose is to ensure that there is detection. There is detection. Explain how the radiation entering the tube through the window is detected. So once the radiations enter now through the window, they have to ionize the argon gas. Radiations enter through the Mika window. I hope you are still able to see. Hopefully, that you can still detect the lesson. Let me check on the networks. Yeah. So we're saying that I can see people are seriously following, and this is great. I'm still encouraging you to invite friends. Kindly invite a classmate, invite a boyfriend, invite a girlfriend to this platform. Share with your friends kindly, classmates, schoolmates. Just invite them. Okay, the radiations enter. Entering through the Mika window, ionize. They have ionization effect. They ionize the argon gas. Ionize the argon gas. After that, Now we have the positive ions attracted by the anode. So the positive ions are attracted by the anode. The positive ions are attracted by the cathode, they move to the cathode. They are attracted by the cathode, while the negative ions are attracted by the anode. Attracted by the anode. So when that happens now, look at the diagram. The positive ones are moving here. The negative ones are moving to the anode. And because we have a potential difference there, we say that current flows. Current flows. And it is recorded. And it is recorded as a pulse. It's recorded as a pulse. So that's how detection happens. State the purpose of the halogen vapor. Halogen vapor acts as a quenching agent, and I'll be explaining what a quenching agent is. So, quenching agent. A quenching agent. It acts as a quenching agent. In simpler terms, it absorbs energy of the positive ions, preventing them from causing secondary ionization. Secondary ionization, which might lead to a force pulse. So a pulse might be recorded thinking that it is from the emission of radiation, yet the positive ions which have been caused by the primary ionization are too heavy and they are too heavy and moving slowly. Because of their weight, they are moving slowly. The positive ions are moving slowly because of their weight to the metal cylinder, which is the cathode. Now, as they move now, they might also, due to their energy, they might also cause secondary ionization. And you know that ionization will also lead to emission of ions, which might get detected. And once they are detected now, we will get false results because we might think that is also emission of particles. We might think that we are dealing with the radioactive substance, yet it is the positive ions from the first ionization which might be causing a second ionization, which we are calling the secondary ionization. So to prevent that, we have a quenching agent. We got a quenching agent, which is the halogen vapor. The halogen vapor. Let's look at part D of this particular question. And thank you so much for following, you guys. Thank you for being around right from the beginning of the lesson up to this far. It's really encouraging. All right. The question is talking about what? We can read it together. While determining the half-life of a certain radioactive material, the graph of a variation of a number of atoms against a number of atoms against time was drawn as shown below. So a graph was drawn as shown below. I hope the graph is clear for you people. I hope it is clear for you people. From wherever you are, please confirm that you can see this graph clearly. I'm trying to project it. I'm trying to focus it to the best of my ability. People are watching even from outside Kenya. Yeah, the graph is now clear. By the way, you can tell us where you are watching us from. Kindly give a message. Give a message. I can see Morey Coley. Thank you so much, a young man from Machakos School. I like that and I sent my greetings to you. Thank you so much, Morey. You can help me invite people to the broadcast. I'm hoping that it is now clear. Yeah, it's now clear. Now, with this graph now, you know, the examiner is telling us to determine the half of the material, to determine the half-life. And what is half-life? According to the, when we were starting this question, we started by defining half-life. So the number of atoms which were initially there, so we just need to know if they started as the initial value was 72. No, this is 70, then this is 72 according to the scale which has been used. According to the scale that has been applied here, we started at 72. So we just want to know the time it took for the number of particles to become 36 times 10 power 2. 36. So this is 30, 31, 32, 33, 34, 35, 36. Yeah, 36 is there. So we move along that until we see where the graph is so that we may know the time. Let me get a ruler. Let me get a ruler so that we may draw a good graph at that point. So we need to move along 36. Along 36 like that. Then down so that we may know the time taken, the corresponding time. So the corresponding time is exactly 20 minutes. We just check. Yeah, 20 minutes. 20 minutes is the corresponding time. 20 minutes is the corresponding time from the graph. Clearly shown that we have read from the graph. It's good to show that you have extracted the values from the graph because the graph has just been drawn for us to make use of it. Wow. This is again another interesting question. A radioactive nuclide of mass number A, atomic number Z, emits a beta particle, an alpha particle, and gamma radiations. State the mass number and the atomic number of the new nuclide. Let me start by drawing what we call the nuclear equation for the reaction that took place. The nuclear equation for the reaction that took place. So let's see. Somebody's called Bruno and following us. Wow, thank you, thank you. Let's say the substance was X. So it is having mass number A and atomic number Z. Then it's going to lose what? It emits beta particles. Beta particles is an electron, whereby the mass number is 0 and the atomic number is -1. Then we are also losing what? A beta particle, which is an helium particle, 4, 2. Then we have gamma radiations, whereby it's just a form of energy, but no significant change in the mass number and the atomic number that may be caused. Remember, the resultant, we have now the new nuclide, which we are calling Y. We can call it Y. So the nuclide Y is supposed to have a mass number such that when we add, we should get A. When we add the mass numbers on the answer side, on the right hand side of the equation, when we add everything, we should get 0. So whatever is here should be such that we get A. We get A. So the unknown here, which we can call let's say there is an unknown T and another unknown here, which you can call R. On the right hand side of the equation and on the left hand side, we must be having equal mass numbers and atomic numbers. So T is going to be, we have a 0 here, 4 and 0. So we subtract them from the other side. A minus 4. Then R, which is the atomic number of the answer, whatever, should be all of them added. They must give us Z. So to remain with R, we have to subtract 2 from that side, and we also add 1, because when 1 goes to the other side, it shall be added. So it will be Z minus 1. This one is mass number. This one is atomic number. Yeah, atomic number. Yeah, confirm that you are seeing everything clearly, kindly. Just give us a comment. Let's know that we are learning together. Let's know that we are together. Please let me know that we are together, ladies and gentlemen. If everything is clear from your side, you can say hi. You can give a comment. Remember that consultation line remains 07 04 15 33 66. This is our consultation line for both physics and mathematics. For both physics and mathematics. Thank you for your comments. Please leave a comment. Let me know that all is well from that side. You are the recipients of everything, not me. You're the ones receiving the knowledge. So let me know whether you are getting everything right. Number 16, now we go to a different topic. All is well. Thank you so much. Number 16, explain the difference between a conductor and a semiconductor using the energy band theory. We usually say that for a conductor, energy band theory. I think I should even give a sketchy diagram. This is the conduction band. This one is the valence band. This one is the energy band. Then we are also having this is a semiconductor. Then for a conductor, we have the conduction band, the valence band, and we have the energy band. Now we say, if this is the conduction band, it is such that together with the valence band, they are overlapping. They are overlapping such that conduction is very free. Thank you, Titus Ngetich. So we say that in the semiconductor, there is a energy band between the conduction band and the valence band, making the material a non-conductor at normal temperatures. So at a normal temperature, while in a conductor, the valence band and the conduction band overlap, leading to no energy band or energy gap. Hence, the material conducts electricity freely. It conducts electricity freely. It just conducts electricity freely. Even at low temperatures, at high temperatures, there is free conduction. State how an increase in temperature affects electrical conductivity of a semiconductor. Increase in temperature. Increase in temperature makes electrons to move from the valence band to the conduction band. Enhancing conductivity. Okay, through the energy gap, by the way, you can say through the energy gap. Through the energy gap. Enhancing conductivity. Enhancing conductivity. That means at normal temperatures, electrons are just settled at the valence band. But once temperatures are increased, those electrons are excited and they can move across the energy gap into the conduction band, and hence conductivity occurs. The second part, we are asked to distinguish between an intrinsic semiconductor and an extrinsic semiconductor. Intrinsic semiconductor is a pure semiconductor. Let me write it well. is a pure semiconductor, while an extrinsic semiconductor is a material into which atoms have been added. Atoms have been added to enhance conductivity. So a pure semiconductor is just waiting for increase in temperature for electrons to get excited. They move across the energy band and conduction takes place. But for an extrinsic semiconductor, this is a material into which atoms have been added onto it to ensure that its conductivity is enhanced. Thank you for following. I can see guys are still around. I'm prompting people to leave comments here. Wow. Bruno. Thank you, Bruno. Thank you, Bruno. Thank you, the guys who are watching us from outside the country, following up with the program. Thank you so much. Okay. Explain how pure silicon. Explain how pure silicon. You know, silicon is a group 4 element, which is naturally a semiconductor. Now, we can make it N-type. And how do we do this? So, we add a pentavalent atom. The examples are, we can have antimony, we can have phosphorus, arsenic, etc. You know, a pentavalent atom will be having 4 valence electrons, 5 pentavalent, 5 valence electrons. So 4 valence electrons are used for bonding, leaving 1 electron vacant. Remember, silicon is a group 4 element. It has 4 valence electrons. But now, the pentavalent atom that we are bonding with, that we are adding here, actually, the process of adding them, substances into a pure semiconductor to boost the conductivity is called doping. And now, depending on the doper, we get either N-type or P-type. Now we want to see how N-type is obtained. To obtain N-type, we are saying that we are adding a pentavalent atom. A pentavalent atom now, the antimony or the phosphorus or the arsenic will come with 5 valence electrons. Now, you've discovered that silicon requires only 4. So 4 will be used for bonding, but there will be an extra electron, which we are calling a vacant electron now. So we will have a vacant electron, whereby now we say that this vacant electron, or this vacant electron, participates or takes place, enhances conductivity. Since it enhances conductivity, and we are also talking of the name now, n-type. Why is it becoming n-type? So electrons now become majority charge carriers. Electrons become the majority charge carriers. Charge carriers. Charge carriers. Charge carriers with holes being minority. With holes being minority. When electrons become majority charge carriers, and they have a net charge which is negative, then we have the name. We have the name n-type because of the negative majority charge carriers. Allow me check something on the electricity, then we continue. Yes. Yeah, I think everything now is sorted. We can now wind up. But generally, we are saying if majority charge carriers are electrons, and electrons have a negative charge, then we get n-type. If we had used a trivalent, we would have gotten holes being majority charge carriers, and hence it would have been a p-type because holes are positive. The figure below shows circuit used for full wave rectification. Insert the missing diodes to make the circuit complete. So the diodes now are going to be D1 and D4 are usually, they are usually forward biased. This one will be this way. We also have this one. Then at this point, it will also be facing this side. And finally, this one. Yeah, and finally, this one. So that is how the diodes are going to be placed to make it a. Yeah. Then the purpose of the capacitor is to smoothen the rectified output. 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 Actually, these are some of the points which are just in the KLB book 4. Even a student should be able to use these papers. You familiarize with a lot of questions. And through that, you should be a very competent student. You'll be responding to these questions very effectively. On the axis provided below, sketch a voltage in volts. Voltage time in seconds. So we're going to have this one this way. The graph again is just in your notes. So for full wave rectification, this is what you should expect. That's how the graph appears. State one property of X-rays, which makes it possible to be used in X-ray photography. X-rays move in straight in straight lines. Moves in straight lines. Then we are told that the figure below shows the features of an X-ray tube. You can see the X-ray tube in a diagram, very clearly drawn. Then the questions flow there. Part 1, name the parts labeled A and B. Name the parts labeled A and B. Let's get to the diagram so that we may know A and B. So A, we can see it is the focusing cathode, or simply the cathode. Then what about B? When you look at B, you discover that B, the arrow for B is pointing at the anode. It's pointing at the anode. Explain the effect of increasing the potential difference across PQ. So across PQ, across PQ now, that is the potential difference, which is giving us current at the filament. So as you increase the potential difference, you also increase the current according to Ohm's law. So increasing the current increases the heating effect. So we will have increased heating effect leading to increased thermionic effect. Thermionic effect. We mean, in other words, more electrons are produced. More electrons are produced, and hence an X-ray or X-ray, let's say X-rays, as X-rays of high intensity are produced. Of high intensity are produced. X-rays of high intensity will be produced. State the property of lead which makes it suitable for use as shielding material in the X-ray tube. Why is lead used? This is due to its high density. It has high density, hence it can absorb. It absorbs stray X-rays. It absorbs stray X-rays. If it was a material of lesser density, it would be penetrated. And X-rays would cause harm to the person operating the machine when they get exposed to the skin. Part C. The work function of sodium is 2.46 electron volts. Determine the threshold frequency for this metal. Determine the threshold frequency for this metal. Then we are given 1 electron volt as 1.6 times 10 power negative 19 joules. We also given a Planck's constant as 6.62 times 10 power negative 34 joule seconds. We usually say that the energy is usually given by HF, but we know that C equals to HF. Wait. Yeah, sure. Energy equals to HF, which means work function is given by H, threshold frequency. So this one can be converted. We take 2.46 multiplied by 10, 1.6, sorry, multiplied by 1.6 times 10 power negative 19. Then this is equal to Planck's constant, 6.62 times 10 power negative 34. Yeah, times 10 power negative 34. Then multiplied by F naught. So we can remain with our F naught now by dividing 2.4. Let me multiply that. 2.46 multiplied by 1.6 times 10 power negative 19. Then divide by 6.62 times 10 power negative 34. This is going to be 5.95 to 2 decimal places multiplied by 10 power positive 14. Being frequency, the units will be hertz. So you just play along with your calculator very effectively. Yeah, and you get the answer. Part D. The graph below is a sketch of photocurrent against the potential difference across the terminals of a photocell when radiated with light of frequency F and intensity. Frequency F and density T. On the same axis, sketch the graph. On the same axis, sketch the graph of the photocurrent against potential difference when the photocell is irradiated with light of higher frequency, but lower intensity. Higher frequency, but lower intensity. So we will have the photocurrent increasing. We'll have the photocurrent increasing so much. So the photocurrent will be a bit higher. Yeah, that's where I expect the other graph. A bit higher because we are increasing the frequency, which means we will have a lot of energy and more photoelectrons will be emitted. Consultation line remains 0704 153366. Yeah, that's it. We got another question here. And actually, we should be winding up now. We are talking about number 18. A light. A light ray from crown glass of refractive index 1.5 into water of refractive index 1.33 at an angle of incidence of 40 degrees as shown. So as shown in the diagram, just as you can see, calculate the angle of refraction in water. We shall say that according to the Snell's law, the first refractive index multiplied by the sine of the first angle equals to the second multiplied by the sine of theta 2. So with this, we will say that 1.52, the sine of 40. This is equal to, when we get to the other medium, 1.33, the sine of unknown angle. So the sine of this unknown angle will be given as 0.7346. And for us to remain with theta 2, we have to take the sine inverse of 0.7346, and this will give us theta 2 is equivalent to 47.27 degrees. 47.27 degrees. By using a ray diagram, show how a converging lens can be used as a magnifying glass. Whereby it can magnifying glass, it can cause a magnified image which is upright. So we usually have we can have the lens here, which is converging, or rather the convex mirror. Then we can draw a straight line here. This straight line will represent what we call the principal axis. Now along this we can have F, Then at an equal distance, we'll have 2F. Then on the other side, at equal distances, F and 2F. Now with this, we say that for a magnified image to be formed, we need the image to be between F and the optical center. Then we draw important rays, very important rays, to ensure that an image is formed. A ray from the tip, which is close and parallel to the principal axis, is going to be refracted through F. Refracted through F. Yeah, refracted through F, like that. A ray through the optical center should pass undeviated through the optical center. Through the optical center, it will pass undeviated. Those are two important rays, but you can see they are diverging the most. So for them to form an image, they have to intersect somewhere, but now using incomplete rays. Yeah, like that. So the image is going to be virtual, but upright and magnified. Virtual, image will be here. Virtual, but upright and magnified. Upright and magnified. The last question. The last question. We are winding up now. So the last question is part C of this, whereby we are told an object placed 20 centimeters in front of a concave lens. Concave lens, very important, with a focal length of 15 centimeters. Determine the position of the image formed. Determine the position of the image formed. So the object is placed 20 centimeters. Object distance 20 centimeters. F is going to be negative 15 centimeters. Now, students are supposed to know that the focal length of a concave lens, which is called diverging lens, is usually negative. Reason being that, it is the distance from the optical center to the principal focus. And the principal focus of a concave lens is a virtual point. Therefore, the length there has to be given a negative according to the realist positive convention. Determine the position of the image formed. V equals to what? We must use the lens formula now. So we're talking of 1 out of 15 negative equals to 1 out of 20 plus 1 out of V. To remain with 1 over V, now we have to take negative 1 over 15. Then we subtract 1 out of 20. This is going to be negative 7 over 60. So what will be V now? Will be negative 8.57 centimeters. This is to mean that the image is virtual. The image is virtual. The same side as object, and it's also virtual. A virtual image, virtual image and form the same side as the object. Remember to subscribe, remember to share, remember to invite friends to Shifting Grades Online School. Remember our consultation line 0704 15 33 66. Success in everything. Thank you.